Okay, so the first section we're going to look at is the second half of 4.2. So we're going to finish that up and do a little bit of sketching, and that's going to finish rational functions with graphing. Tomorrow we're still doing rational functions, but it's going to be more algebra. How do you solve an equation? It's a little different way to view that type of graph. But that's pretty much what we do with all the different types. We usually look at how they look, and then we look at how you solve them. So the kind of problems that we did last time we had class, the degree in the numerator was always less than or equal to the denominator. And whenever that happens, you have horizontal asymptotes. Right? So a problem we might have done is something like, let's say, 3x squared plus 4x minus 5. And let's divide that by x cubed minus 7. If we were going to analyze that by finding the asymptotes, graphing it, and all that, that would have been a problem we did last time. Because the degree in the top is a 2, degree in the bottom is a 3. So the degree in the top is less than the bottom. Another problem we could have looked at last time would have been something like that. Still a problem that would have fallen into the category where the degree in the top is less than or equal to the bottom, because that time it's equal. What's the degree in the top for the problem I just wrote down on the right? Ryan?
2.
2, and the degree in the bottom?
2.
It's also 2. Yep. So again, result here is horizontal asymptotes. But when we flip that around so that the degree in the top is bigger than the bottom, okay, not less than or equal to, but bigger, then what happens is the horizontal asymptote goes away. Okay. It's going to be replaced by something else. So that's important to remember. When the degree in the top is larger, you will not have a horizontal asymptote. It will be replaced by something else. What it is replaced by, well, the complexity of what it's replaced by depends on the degrees. And not just the degrees, but the difference between them. Okay. That's going to dictate the complexity of the graph. So any question on the difference between the kind of problem we're going to do now and then the kind we did before? So before, all our asymptotes were always horizontals and verticals. Still going to have verticals today. That's not going to go away, but the horizontals will. Okay, so what is the horizontal going to be replaced with? It's going to be replaced with, bless you, this thing called an end behavior asymptote. We're going to call it EBA. Sounds similar to something we've done before, EBM, but it is different. Okay? At least the process of how you find it is different. So let's say we had two rational functions. Okay? I don't know what they're going to be in the problem we do, but let's just call the top h of x, and we'll call the bottom g of x. When we do a real question, it'll be something like that. There's one in the top, there's one in the bottom. When you divide these two things, okay, you will get a quotient and a remainder. And because they're polynomials, it is possible that the quotient and remainder have letters. That's why I wrote them as functions. It's also possible the remainder, sometimes it's just a number, it doesn't have a letter. Okay. And I want to just kind of review, we did this with numbers, but when I take, let's say 13 and divide by 5, what's my quotient there? Take 13 and divide by 5. 2, yeah. And what's my remainder? 3. How can you write that answer as something that would look like a number? Because writing it like this, that is an answer, but that's not a number. That's a Q colon and an R colon. How do you rearrange that as a number? It's going to involve those two things and one of the original numbers. Yep.
2 and 3/5.
2 plus 3/5, right? Quotient plus remainder over divisor. That's how you end up with a mixed number. Okay, I'm going to do exactly the same thing here. Quotient plus remainder over my original denominator, divisor. The part that we're interested in when we do out the long division isn't the remainder over the divisor. We don't care about that part. The part that we care about is the quotient. And the quotient is the EBA. That's all there is to it. The quotient is the EBA. So it's using a process we already know how to do, either long division or synthetic division. And we're just going to call the result something different. Instead of calling it the quotient, we're going to call it the EBA. Okay, but it's the same, it's exactly the same thing. Now I say you can find the quotient using either long division or synthetic division. Long division you can use all the time. To use synthetic division, what format does the denominator have to be in? Yeah?
Or x minus?
Yes, it has to be x minus a number. Okay. That's the only time you can use synthetic. So technically you could also do x plus if you rewrite it as minus or negative. Okay. Synthetic is what I'm going to do as long as I can. If I have a problem that's more complicated, then I have to do long division. Right, so let's look at this one. It says find the quotient, the remainder, and the EBA. So f of x is 2x cubed minus 4x squared plus 3 over x minus 2. Okay, so first question, why does this fit into the type of problem that we're looking at today, but it's not the type of problem we would have done last week? What's different about this? Yeah.
The first number in the top has a higher power than the one at the bottom, right?
And what do you call that number? It's the...
Leading coefficient?
No, we don't look at the leading coefficient. That's the number in front of x. Yep, the degree. So the degree in the top is larger than the bottom. And generally your polynomial should be in descending order, but even if I did something like this, that is exactly the same numerator. You can't always go by the first exponent. Okay, you've got to go by the term with the highest. Okay. Now, the degree in the top is a 3, the degree in the bottom is a 1. What's the difference? Courtney?
Can you repeat that?
What's the difference in the degrees between the numerator and denominator?
Well, the numerator is x to the third, and the denominator is just x, so it's 2.
So that's a difference of 2. That means when we find the EBA, this EBA is going to have an exponent of 2. The further apart these two degrees are, the more complicated it is to draw the EBA. But these are 2 apart, so it's going to be a degree 2. And what do we call the graph of something that's a degree 2? It's a quadratic equation, but the graph is called a parabola. So the graph here is going to have a parabolic shape to it, at least on the ends of the graph. What it does in the middle, that's not what this is going to tell you. Okay? This is end behavior. What's happening on the very far left and right edges of the graph. That's what we're about to figure out. We still have to figure out what's happening in the middle. That's where vertical asymptotes and plotting some points with the calculator will come in. All right, so let's figure out our EBA. To find the EBA, we're going to do out the division. Would this be long division, or could I use synthetic division?
Synthetic.
Yeah, I could use synthetic. What number would go on the outside?
2.
2. And how about my numbers on the inside?
2, -4, 0, 1, 3.
2, -4. Make sure you fill in that 0 for the x term. And then +3. And once I get my result, what part of the result am I concerned with right now if I'm trying to find the EVA?
Quotient.
Right, the quotient. We're going to find some other things too, but specifically for the EVA, I want the quotient. So bring down our 2, multiply, add those up, multiply, add those up. And technically I can stop there if all I need is the EVA, because the next number is going to be my what? It's going to be my remainder. 2 times 0 is 0, and +3. Right, so we got enough information now to write down everything they want. Let's start with the quotient. Okay, what is the quotient here? Yeah? 2x squared. Quotient is generally just written as an expression. A quotient is not an equation. So you should not have an equal sign in a quotient. Okay, remainder. What's my remainder? 3. Again, same thing. Remainder is an expression. It could be a numeric expression or a variable expression, but it's not an equation. Okay, EVA. EVA is an equation. It's something you could type in on the calculator and start to see what the ends of the graph look like. The equation always starts with y equals. And now, what would be on the other side of that equation for my EVA? Yeah.
Quotient.
The quotient, 2x squared. So yes, the quotient and the EVA are pretty much the same thing. It's just a matter of how you write the answer. Is it an equation or an expression? And that's everything they wanted. Any question on that? So what we're going to do now is we are going to talk a little bit about the difference between the EVA and the EVM. Okay, EVA is what we're doing today. EVA doesn't exist with the kind of problems we did before, because when the degree in the bottom is bigger than the top, you can't do long division. It doesn't fit into it. The degree in the top has to be larger to have an EVA. All right, so the difference between the EVM and the EVA. The main difference is how you find it. The EVM is when you take the highest degree term in the top, divide by the highest degree term in the bottom. That's pretty quick. The EVA is when you do division. Sometimes, each of those processes I just explained will result in the same answer. So the EVM and the EVA can be the same. In the problem that we just did, they would be. The only reason that they would come out the same is because this was a 0 and that was a 0. That usually doesn't happen. Usually when you're finding your quotient, you have numbers other than 0. But because they both came out to zeros, in this case, the EVM and the EVA would be the same. But you wouldn't necessarily know that just by looking at a problem. That's not something you can identify really unless you do the long division. So, problems that we did last week. Degree of the numerator was always less than or equal to the degree of the denominator. That gave us two different kinds of asymptotes, horizontal and vertical. And those are the only ones we ever had to think about. Both of those asymptotes, horizontal and vertical, are straight line asymptotes. When the degree in the top is bigger, asymptotes can start to curve. So instead of having a line that your graph comes down and like gets closer and closer and closer to, you can actually have something dotted that's curving, and your graph is getting closer to something that's curved. And that's what I'm going to show you in the problem that we just did. The bigger the difference in the degrees between the top and the bottom, the higher of the degree of the EVA. So if you had like a 5 in the top and a 2 in the bottom, that's a difference of 3. That means your EBA is going to have an exponent of 3. That's a cubic. That's a little bit more complicated than the one we're doing, which is going to be quadratic. In general, I wouldn't expect you to worry about graphing a problem that has an EBA higher than 2. Would I have you find an EBA higher than 2? Sure. Graph it? No. Higher than 2. But 2 itself, we're going to do that right now. Okay. Any questions on those 3 things? All right, so what I want to do now is just verify what we just found. Let's graph the EBA. Let's graph the question that they gave us. And let's see if the graph is getting closer and closer to what we think the EBA is. Okay, so I need to go back and I need to look at the original problem again. Okay, so let's type that in. As I type that in on the calculator, what do I need to make sure I do with the numerator and denominator? If I don't do this, it's probably not going to graph it correctly. Yeah?
Both in parentheses.
Right, because the top is a trinomial, the bottom's a binomial. You have multiple terms. You need parentheses. So we've got 2x cubed minus 4x squared plus 3 divided by x minus 2. Now I might have to zoom out a little bit. I'm not sure yet. Okay. On y2, I'm going to type in the EBA, 2x squared. And the idea is that as I zoom out and look further and further on the left and right edges of the picture, the blue graph and the red graph are going to get very close to each other. They're going to kind of parallel each other on a curve and get closer all the time. The red graph will have no meaning when we're in the middle. It's not going to tell us anything in the middle. In the middle, something weird is going to happen. Okay, so I need to zoom out a little bit, but I think you can start to see it here. So look at, you can only see the left edge. You do need to see the right edge, which I'll fix in a second. Okay, but look at that left edge. Notice the blue and the red one, they are paralleling each other, but they're getting closer and closer and closer as you head to the left. Can people see that okay? Okay. Now, the same thing should be happening on the right. When you have an EBA that has an exponent of 2, it's supposed to look like a parabola. This blue graph should be a parabola, but I can't see the other part because it's probably up off the screen. So what I'm going to do is set my Ymax. Let's try like 40. It's important to find that other part because sometimes what's hidden off the screen is important. Like in this one. For example, if I asked you how many local minimums does this graph have? If you look at that original problem, you might just say, there's a low point right there. Remember, a minimum is kind of like if you pour water in the graph, it's where the water would collect. It's like a hole, like a divot in the graph. Okay. So you'd say, well, there's one local minimum there. But if you zoom out, you see that there's another one up higher. Okay, so you do have to know to zoom out and look for it. But now you can see the parabola shape on each end of the graph. The blue and the red are getting closer and closer on the ends. Okay, so the graph in blue, it's kind of like a parabola that wants to be connected, but it can't. Because if you plug in the number 2, what would happen in f of x? We'd be dividing by 0, which is a vertical asymptote. So that graph in blue cannot cross the vertical asymptote. So what happens is it's kind of like somebody took the graph in blue, they cut it, and then they took each piece of the parabola and bent one part down and they bent the other part up. And that's basically what's happening. So now we want to see how to sketch something like that. Okay. So we've done the example. We verified that 2x squared looks like it's the EBA. What would it look like if it wasn't the EBA? Well, let me type in something that's not right. Let me change the EBA to 5x squared. Hopefully, as long as I changed it enough, it's not going to look like the blue and the red one are getting closer and closer anymore. Yeah, that doesn't look good at all. I can tell, actually, when I look at it on the left, now it looks like the blue and the red one are widening. They're getting further apart. So 5x squared is definitely not the EDA. Okay, so that's what it would look like if you make a mistake. All right, now we're going to sketch it. The only problem is these numbers, I had to go all the way to y max of 40. So I scaled my y-axis to go by 2s. I should probably go even higher, but we'll try to do the best we can going by 2s. Okay, so when you want to sketch a graph where the degree in the top is larger than the bottom, the first thing you want to do is find the EBA. Okay, so that would mean now we do the long division, but we already did it. Okay, it's the same question we just did. So we're going to sketch that EBA, but we'll sketch it by hand, and we'll make it dotted so we remember it's an asymptote.
Sorry to interrupt. Can I steal a can of cola for a minute?
Sure. Yeah, no problem. Okay, if you don't remember how to sketch the parabola, just pick some points. If x is 0, y is 0. What about if x is 1? What's y going to be? Oh, Amaya? What's 1 squared? Times 2? 2. So if x is 1, we get 2. If x is 1, we get 2. How about if x is 2? What would that give me for a y value? Well, Moises? 2 squared is 4 times 2 is 8. So we get 2, 8. Let's do one more. 3. 3 we get, yeah, 18. Okay, so 3, 18. And because this parabola hasn't been shifted left or right, the line of symmetry is the y-axis. So we can reflect all those points over the y-axis to get the other half. So -1, we're going to go 2, 3, 3. Okay, and now draw that the best you can as a dotted line. Remember, that's not the graph, that's the asymptote for the graph. Good enough. Okay, so we've got the end behavior asymptote. What's another kind of asymptote that this graph is going to have? Yeah, vertical. Okay, so let's find the vertical asymptote. Dex, how does the equation of a vertical asymptote always start?
Is it with positive or negative?
Nope, with a letter. It's going to start with a letter. Nick? Yes, it's always going to be x equals. And as long as you don't have any factors, common factors in the numerator and denominator, it's always going to be the roots of the denominator. This one doesn't have any common factors. If you really wanted to figure that out, well, actually we already did. If this was a common factor when we divided it, what would have happened? We would have gotten a remainder of 0. But when we found the EDA, we did not get a remainder of 0. So we know that the bottom is not a common factor of the top, which means any kind of hole is out of the question. Right, so it is definitely a vertical asymptote. And it's a vertical asymptote at what number? Yeah, 2. So now let's draw in that. So now we've got our vertical asymptote. We've got our EBA. Should we look for a horizontal asymptote? Why not? There isn't one. You cannot have a horizontal asymptote when the degree in the top is bigger than the bottom. Can't happen. That EBA replaced the horizontal asymptote. Now we need some points. Okay, so we're going to go to our table, and we're going to plot as many points as you think you need to get a good sketch. Okay, we don't need the EBA anymore. I just need the original problem. Okay, don't plug in 2, because you're going to get an error. What would be a number that's a little bit smaller than 2? Lucas?
1.99.
Sure. 1.99. I'm at almost negative 3,000. Okay. So basically, we're heading down to what? Just before the number 2. We're heading down to negative infinity. So put your dot as low as you can. Let's check a value on the other side of the asymptote. What would be a good value to check on the other side of the asymptote? Yeah. 2.001. We're at 3,000. So on the other side of the vertical asymptote, we are approaching. Yeah, we're approaching infinity. So put the dot as high as you can. Okay, now we're going to need some more points. Okay, let's start by checking to the left of the vertical asymptote and figure out what's going on in this area. So let's try. We already did something really close to negative 2. Let's do negative 1. Okay, that I can graph. Negative 1, 1. Remember, my y-axis goes by 2, so that's up half a block on my graph. So negative 1, and then up half a block. That looks good. Let's do 0. We can do that one. So there's my y-intercept. 0, negative 1.5. So probably about right there. Because remember, if I went right to the line, that would be negative 2. So just before the line. And then let's do, we could try negative 3. We're going to start to go off the graph pretty quick, though. Yeah, that's already up at 17.4. So negative 3. We're all the way up at like 17.4. All right, so we can kind of see what's happening. To get the exact curve, you might need another point in there somewhere. Let's try 1, because we know that it does have a little bit of a curve to it. 1, negative 1. So right 1, down half a block. Okay, now I can see that it went back up a little bit. If you didn't do that other point, you might just think the graph goes like that. It doesn't. It has a little bit of a curve back up, and it gets like a maximum in that area right there. All right, so let's sketch that. So you're going to stay very close to the asymptote. Go through your points. And then continue getting closer and closer. Okay, so there's the left side. And now the right side is going to be a little tricky because our graph only goes to 20. So what we want to do now is try maybe like we did 2. We could try 3. Let's see. It's going to be pretty high. Okay, 321. Just off my graph a little bit. So 3 is up at 21. If you did like 2.5, let's see where we're at there. Okay, 18.5. Okay, so that's a little bit lower. That's on my graph. So 2.5, 18.5. Okay, so I've got those 3 blue dots. I know that it can't cross the vertical. It's not going to cross the EBA. So it's going to be kind of trapped in this section right here. And it has to stay very close to both of them. So it's going to kind of come down. It's going to curve through that point, and it's going to keep going. So this part right here and this part over here, the 2 parts that I just made a little bit bolder in blue, that's what the EBA is giving me. The part in the middle, I've got to do a little bit of trial and error and play with the vertical asymptote to get that just right. But from our sketch we did earlier, you can see what we did by hand. Looks pretty good. Setting your y max to 20 on the graph, I don't think that would really give you a good picture, because all you would see is that little part right there. Okay, I think going to 40 is a better view. Okay, and that's about as complicated of a rational function as we are going to do. Any questions on that one? Especially how to find like EDA, vertical asymptotes, things like that. Okay, I did find the intercepts here. Definitely, well, I found the y-intercept by plugging in 0 for x. I did not find the x-intercept. I know it crosses the x-axis, but I didn't find it. There's two ways I could have. I could try to set the numerator equal to 0. That's one way to do it. But that's a cubic, and now I'm getting into a pretty messy equation to solve. So honestly, it's probably not worth the effort just to get that 1 point, which doesn't really tell me a lot. If I was asking you what is the root, then I'd just say use the graphing calculator to find it. But I wouldn't say that that's a very critical point that you need for this problem. All right, so let's try this one. So it says determine the EVA, the vertical asymptotes, and make a sketch. Okay, what's the degree in the top this time? 3. What's the degree in the bottom? 2. That's a difference of how much? 1. So this is a little bit less complicated than the last one in terms of the EVA. It's going to be a degree 1. But degree 1 isn't as simple as a horizontal line. What would you get if you graph a polynomial that's degree 1?
Linear.
It would be linear. But how would it differ from something that's horizontal?
It would have a slope.
It would have a slope to it, yes. So what we're going to get here is a line that's on a slope. That's going to be our vertical asymptote. So a little bit easier in the sense it's back to linear, but it's not as simple as horizontal because it's not just going to go left to right. It's going to be slanted. Okay, so I need to find the EVA. Let's do that first. When I find the EVA, can I do it with synthetic division? What do we think? Maddie, what do you think? No, why not?
Because it's not a linear.
Right, it has to be linear in the bottom if you're using synthetic division. So that means we have to use what? You got to use long division. But luckily, the degree difference is only a 1. So there's not going to be that many rounds of long division. It's going to be like two rounds, and that'll be it. Okay, so we've got x squared plus 2x minus 3 divided into 2x cubed plus 7x squared. What would be my next term after that?
Plus 0.
Plus 0x. And then minus 4. Okay, so 2x cubed divided by x squared is going to leave me with 2x. Multiply it back out. 2x cubed. 2x times 2x is 4x squared. And now what do we do with the columns when we do long division? Well, Aiden, what do I do with the columns?
Like after.
So it's our next step in the long division. We're gonna-
To subtract.
Yep. So we're going to
plus-
subtract.
Yeah, just subtract.
So we subtract the columns. These are gone. 7x squared minus 4x squared gives me 3x squared. And now you can bring down the rest if you want, but I'm not looking for the remainder, so I don't need to. I'm just going to take 3x squared and divide by x squared. And what does that give me?
3x.
We already have the term with the x, so the next term isn't going to have an x. 3. Yep. And that is my quotient. It's not quite my EDA, but it is my quotient. How would I write that as an EBA? Oh, Mike?
X equals 3x squared, or y equals 3x squared.
So it is y equals. What is that 3x squared? Well, it's actually 3x squared.
I'm sorry.
I can bring down this, and then if I multiplied it all out, 3x squared.
It'd be 2x plus 3.
Yeah, it would just be 2x plus 3. So we don't even need to do all this and subtract the columns unless we want the remainder. But yeah, it would just be y equals 2x plus 3. That's my EDA. Okay, Cecilia, how would I graph that?
Well, first you could make a table, find your points of the EVA.
Yeah, you could make a table. Since this one is linear, we could just think about it as y equals mx plus b. If we didn't want to make a table, because that'll be a little bit faster. So when I write down, what is the plus 3 there?
That would be like on the graph.
So when you think about an equation in y equals mx plus b form, the plus 3 is telling me something about the line. It's the blank of the line.
With the y-intercept?
Y-intercept. Yep. So what I would do first is put a dot at 3. And what else is important there that's going to help me get another dot on this line? Yeah.
The 2x is the slope.
Yeah, the 2 is the slope. And how would you use the 2 to get another dot on the line?
Well, if it's the slope, it would be like up to over 1, right?
Can you be more specific?
Not really sure how.
Can you be more specific than up to over 1? I could interpret that a few different ways. Yeah.
Could be like 5, 1, like over right 1. Right
So-
1 up to.
Up to right 1, yes. Yep. So we're going to go up to and to the right 1. Do not go to the left 1. That would give you a negative slope. This is up and to the right. Okay. You could do back. We can go backwards the other way in a minute. But if you start by saying up, then you have to say right. If you had said down, then we could also go left. You can do as many dots as you want, but there's your asymptote. Okay, so that's called a slant asymptote because it's on a slant. So not as complicated as a quadratic asymptote, but not quite as simple as a horizontal. Okay, so we got the EDA. They also asked us to find the vertical asymptotes. Okay, how do you find vertical asymptotes? This one's not quite as easy because of the way the bottom is set up. What do we have to do? Maddie? Yeah, we need to factor, or worst case scenario, we're going to have to use quadratic formula. But that bottom, we can try to factor it. So we would have x and x, and two numbers that multiply to give us 3. Well, we're going to use 1 and 3. And what about my signs? Positives, negatives, or one of each?
-1 is positive 3, 4, vice
Alright.
versa.
Positive 3,
Yes.
like that. So we got x squared, that gives me plus 3 minus 1 is plus 2. That's perfect. Okay. So we have factored it. We could check for common factors with the numerator and denominator, but I'll just tell you on this one, those two factors you just found are not factors of the numerator. We'd have to check it with synthetic division. That'd be the quickest. Well, actually, we could also use the remainder theorem. If you just plug in the number after the minus sign into the top, that would tell you what the remainder is. So if you plug in 1, it's the number after the minus sign, you get 2 plus 7 minus 4. 2 plus 7 minus 4 is not 0. Okay, so that's not a factor. And if you plug in -3, the number that would be after the minus sign in the second factor, -3 plugged in, it doesn't give you 0 either. Right? So there are no common factors. So we're going to have 2 vertical asymptotes. What are they? Yeah.
X equals 1 and X equals
Yeah. And when you're graphing problems like we're doing today, that's pretty much all that we do. Okay, just find all the asymptotes and then we plot points. Okay, so let's do x equals 1 and x equals -3. So this is going to divide our graph into 3 sections. So it's going to be 3 separate pieces. Okay, so let's get it ready so we can start using the table. So we've got 2x cubed plus 7x squared minus 4. And we're going to divide by x squared plus 2x minus 3. Okay, give me a couple points that I could plug in to check out the behavior at the -3 asymptote. What would be a good value to plug in? Yeah.
-2.999.
-2.999. All right. Let's keep going before we graph all this. Can you give me another one?
-3.001.
-3.001. Okay, that's good. Checks out the behavior over there. So on the right side of the asymptote, we're heading down. On the left side of the asymptote, up. So up, down. Okay, we got that. How about somebody else give me some points to check out the other asymptote? Yeah. All right, so let's do 0.999 and one more.
1.001.
Perfect. All right, so on the left side, we're heading down. On the right side, we're heading up. So left side, down. Right side, up. Okay. Now we need to check out, let's check out a little bit more in the middle. Let's see if we can get this middle section. What would be another good x value I could pick that would give me a point between the asymptotes? Yep. Check.
-1.
-1. All right, -1, -1/4. Let's do that one. -1, -1/4. I'd say 0 would be a good one. 0, 1.3. So that's a good one. And I think that's enough for me to see what's happening in the middle. We got to connect all those green dots. We can't touch any of the asymptotes, and everything has to have a curve to it. So it's going to kind of come up, start to curve, and it wants to kind of keep going this way, but it can't. So it's going to curve and come back down. So that's basically what the middle is going to look like. Let's do the left. I think that's going to be the next easiest one because we got plenty of graph. What would be a good x value to figure out what's happening to the left of -3? Yeah.
-3.1.
Well, we already know what's happening that close to it. We're going to go to infinity.
-4.
Okay, so let's do -4. -4, -4. 1, 2, 3, 4. 1, 2, 3, 4. And for me, that's enough. I see this green dot up here. I see that one down there. I know I have to connect them. Keep my graph curved. Don't touch any of the dotted lines. So it's going to kind of come down. Stay very close to it. Curve. And then start getting closer to it again. Okay, So that's what's happening in the left section. Okay, and now the right section. Well, the right section, unfortunately, it's going to be trapped in that area right there. So we don't have a lot of graph to kind of play with here. What would be a good x value I could try? 3. I think 3 is going to be really high. Well, oh no, it's not. It still fits. 9.4. So it's right on the edge. Okay, so 3, 9.4. So 9.4, right about there. So we can't go any higher than 3. Okay, if you try like 4 or 5, it's way too high now. Maybe one more point, somewhere in there. Yeah?
2.
2? Yeah, I think 2 is going to be perfect. That should fit. 2, 8. Good. 2, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so now connect all those green dots and just don't touch the asymptotes. And it comes down, curves, and that part's going to keep going like that. So as you zoom out and look at this graph, the ends of the graph are going to level out to a slanted line that has a slope of 2 and a y-intercept of 3. That's the part that you're looking at right here, and the part that you're looking at right there. All the stuff in the middle, the EVA doesn't help you with. You got to investigate that by putting the asymptotes that are vertical, and then check some points near them. All right, let's see how we did. I'm just going to set my y max. I'm going to go a little higher than 10. I'm going to go up to like 25. And I think that'll give a good picture. Okay, so there's that left part. There's the middle part. And there's more of the right part that you can see. If you want to check your EBA and see if it looks good, type it in. 2x plus 3. Okay, so looking at that, let's put this like this. Does it look like the blue and the red are getting closer and closer together? Yeah, further out you go. Yeah, definitely. By the time you get out to like x equals 10 or 11, it looks like they're almost identical. Remember, they're not. It's just extremely close. Okay, and the other way too. I didn't zoom down, but you can see it's getting closer. Okay, any question on that one? Okay, so that's an example when the degrees are 1 apart. You've got a slant asymptote. When the degrees are 2 apart, you've got a quadratic asymptote. A quadratic asymptote or lower is what you would be expected to know how to graph. Anything higher than a quadratic EVA, I might ask you to find it by doing division, but I wouldn't ask you to sketch it. Okay. I don't want to sketch this one. I just want you to tell me what kind of asymptote. Do you think, would this have a quadratic asymptote, a slant asymptote, or something we haven't even talked about, like a higher cubic asymptote or something?
Slant.
Right. This would be a slant, because the degree in the top is a 2, degree in the bottom is a 1. That's a difference of 1. And so it's a slant asymptote like the last problem, but it's going to be simpler to find the EBA. How come?
Even though it's a difference of 1, they're not as high of degrees in the first place.
So what can you use to find the slant asymptote?
Synthetic division.
You can use synthetic division. And the other thing that would make this one a little simpler than that one is how many values can you plug into the denominator to make it 0?
1.
1. How many values could you plug into the denominator on this one to make it 0?
2.
2. So you're only going to have 1 vertical asymptote and 1 slant. So I'm not going to graph the whole thing in detail, but what you could get is something like this. You're going to get a vertical, you're going to get a slant, and then your graph could end up being in those 2 parts, basically like that. That's the idea of what I think I would expect to happen in this problem. So it is a lot simpler. Okay, let's look at this one. This one we're not going to sketch by hand. There's a lot going on, a lot of terms. What I want to do is graph it. I want to look for what I call hidden behavior. Okay, what does that mean? That's kind of a vague thing. Look for hidden behavior. Well, hidden behavior could be something that's off the screen that you can't see, or it could be something on the screen that you can see, but you can't see it in enough detail with a standard window to really know what's going on. Okay. Let's type that in and see what it looks like. First of all, what kind of asymptote is this going to have for an
Slant.
EDA? Yep, it will be a slant. So we've got 2x to the 4th, let's see, plus 7x cubed, plus 7x squared, plus 2x. That's the first thing I'm going to do. I'm going to try to zoom out enough that I can see the slant asymptote. Bless you. X squared minus x plus 50. Okay, so what am I going to need to do that? Well, I don't really know. So let's start with zoom 6. Okay, let's. I want to look a little further down and to the left, and I want to look a little further up and to the right. So let's do. Let's just change one thing at a time. Let's try making the y min like negative 30, and let's make the y max positive 30. It should allow me to see a little bit lower. Okay, now I see the slant asymptote. Couldn't quite see it as well before, but I think now you can see it. Okay, so there's your graph. And I would say the slant asymptote is somewhere kind of like that. Notice what's happening here is it's kind of coming up, and then it almost starts to take a curve back down a little bit and become less steep. And that's where the asymptote is coming in. So probably right like that, and I think that would curve down even just a little bit more and start getting closer and closer. But there's the idea, I think, of where my slant asymptote would be. It just has to curve a little bit more, and then it'll start getting closer. All right. I would say overall that's a good big picture. But does anybody see something there that maybe I want to zoom in and check out a little bit more? There's nothing more that's going to happen on the left and the right. This is just going to keep going that way. That's going to go that way. That's going to go like that. And that's probably going to curve just a little bit more down and then start to have a pretty constant slope. But there's something there I think I want to look at a little closer. Yep.
What appears to be a flat in the middle of the problem.
Yeah, let's check out this right here. So if I wanted to check that out, let's make a new graph. It looks like I'm going to use an x from -3 to +1. So let's do -3. That'll zoom me in on my x. And what about my y min and max?
Probably
To zoom in on that box.
It would be approximately like negative and positive 2.
Yeah, negative +2. I'm even going to go a little bit more. I'm going to do negative and +1 just to see if I can start to zoom in. And now this whole screen is just what's in that red box on the left. Okay, so I'll take that, I'll put that on the board, and let's look at that. Okay, so now, what are you starting to notice there? Yeah.
that little like bump
Yeah, it does. It looks like there is a little bit of a dip there, like it is going under the axis. Well, then what I would do is let's do the same thing we just did again. Zoom in on this section. So what do you think I could use for a y min and y max now, keeping in mind we had negative 1 to 1? I want to go down to that. Yeah?
Maybe 0.25 and negative 0.25.
Yeah, you could do that. I'm going to go even more. I'm going to go all the way down to like negative 0.1. So I'm going to really zoom in. And the point here is so you can see something that you couldn't see before. So that part that looked really flat originally, when you zoom in a lot, you notice that
Is it
it's not flat, right?
low?
It's not
local
flat at all.
minimum?
Yeah, we've got all kinds of local minimums and maximums happening there. Things that you would never see if you didn't zoom in that much. In fact, how many times does it look like it crosses the x-axis?
4 times.
Yeah, it crosses 4 times. So the point here is sometimes you need 2 windows to see what's going on. You need a big window, like we had in the original problem, to be able to see the slant asymptotes. But then, to really investigate what's happening near the axis, you need a different window to zoom in quite a bit more. Okay, so that's what I mean by looking for hidden behavior. Okay, any questions on that? All right, so that pretty much finishes up 4.2. Right, so that's all on the graphing rational functions. Tomorrow we'll finish rational functions, but it's going to be on solving equations. So it'll be mostly solving algebraically. We might look at a little bit graphically, but we are going to do quite a bit algebraically. And that'll finish rational. And then Wednesday we'll do radical. That's where you have square roots in equations. And because we don't go into as much depth with radicals, we're going to solve equations and do some graphing, I think, on the same day. We'll do a little bit of both. All right, so that's the homework for tonight. So it's part 2 of the 4.2 lesson, 38 to 42, 45 to 47, and then 51, 52, 55, 62, and 63.